Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today we're learning about principal component analysis. Principal component analysis, or PCA for short, is an example of unsupervised learning where we are looking for patterns and structure in datasets which are often quite large with many dimensions. It's designed to be used as part of an exploratory data analysis to learn more about the data that we have. One way to think about the method is that we want to find a low-dimensional representation of the data that allows us to visualize any groupings. We can then further investigate those groupings through a technique known as clustering. This video will focus on the first part, the analysis that identifies the principal components of the data that lead to these distinct groupings. If you'd like to learn more about clustering, then make sure to check out the Data Analyst Masters course on Simplilearn. You'll find all of the relevant links below, as well as a 20% discount code TRM20. Let's consider the following fictional data set. So suppose I only have two variables, to keep this nice and simple, x1 and x2, and after collecting my data, we have something like the following. So we have some points around here, let's say, and another set of points perhaps over here. So again, this is obviously exaggerated to exemplify the method, but we can see here there are two very clear, distinct groupings of the data. But at the moment, we can't actually use either of our current variables, x1 or x2, to identify to which group a data point or which cluster a data point may belong. So for example, if we were to take this data and flatten it onto x1, we would see a range of values between, let's call them A and B. And if we were to take the other group and flatten this, or just look at the x1 value, we would again see between C and D, but we have this overlap between A and D. So there's no clear distinction between the two groups based on x1, despite them very clearly in this representation being distinct groups. And we'd see the same thing over here on the x2 axis. So we'd have sort of values here between, let's call these C1 and D1, and then over here, these would be A1 and B1. So we can't just rely on the variables that already exist in the data set. They alone, x1 and x2 alone, will not allow us to distinguish between those two groupings. And this is where PCA, principal component analysis, is really going to help. Here, the two groupings could actually be easily identified by rotating the axes. So if we were to perform some kind of rotation, which we will work out in just a moment, to get some new axis, let's call this Z2, and then we want another orthogonal axis, so it's still at a right angle, and this is going to be Z1. Then under this transformation, or under this rotation of our axes, we can now very clearly see that this first group here is between, let's call it A2 and B2 along the Z1 axis. And our second group over here is now between C2 and D2 along that Z1 axis. So we have very clearly divided up the data into these two clusterings, and we could, if we wanted to, sort of make a prediction or an understanding of a new data point purely based on its value along the Z1 axis. We would expect it to fall into one of these two clusters. Now, if we think about what we have done here from a geometric perspective, then we have rotated the axes. But what that means is actually just saying that our new axis, Z1, is just going to be some linear combination of our previous two axes. Alpha 1, which is unknown, times the x1 variable, and alpha 2 times the x2 variable. And again, because I have exaggerated this example a little bit, this is clearly just a 45-degree rotation of our axes. So we can say that this is actually now just going to be 1 over root 2 times x1 plus 1 over root 2 times x2. And the reason here that I have picked 1 over root 2 for both of these coefficients is to ensure that alpha 1 squared plus alpha 2 squared is equal to 1. So if we think of our coefficients alpha as a vector, so if we say alpha is alpha 1, alpha 2, where they are our coefficients in this linear combination of our variables, then what we've done here is made this a unit vector. At this point, you can just think of that as a convention, but we will see later when we do the derivation of the full method of principal component analysis, this is actually going to be key, this idea about constraining the model to be a unit vector. It, of course, doesn't actually matter in the sense of the rotation, as long as we have the same value for alpha 1 and alpha 2, that will result in this 45-degree diagonal axis, which perfectly divides our data up in this example. So just to summarize what we've seen in this simple example, we had two clear clusters in our data set, and we were able to represent it in 2D because we only had two variables, x1 and x2. Of course, most data sets will have a very large number of variables, and they're the ones we're interested in. So we will, of course, come to that in a moment. But in our simple example, we just have these two variables, and we had these two clear clusters. And so what we wanted to do, or what we have done, is rotate the axes, which we did by finding a linear combination. So some amount of each variable added to one another, and again, all of these are linear to the power 1 for each variable. So we take a linear combination of our variables to find our principal component, which is z1, and that gives us our new axis, which is actually now going to perfectly separate the data into these two clusters along this axis. Now for the more general method of principal component analysis, where we will have many more variables and therefore cannot easily visualize the clusters, we want to take a similar approach. So what we want to do is find a linear combination of all of our variables. So this is going to go up to some large number. There could be 100 variables, for example. And what we want to do is take a linear combination of those variables in order to rotate our axes and be able to visualize the data and spot patterns that we might not otherwise be able to identify. So really what we're trying to do through principal component analysis, in some sense, is to find a small number of dimensions that represent the key patterns in the larger data set. And in particular, we want those dimensions to be as interesting as possible. The air quotes were there because we need to define what do we mean by interesting. Now, if we go back to our simple example, interesting here meant identification of these groupings or clusters or patterns in the data. And so it turns out that to distinguish or to identify these clusters, interesting actually means maximizing the variance along our principal component axes. So what do we have here variance-wise? If we were to approximately take the mean somewhere in the middle here, then the variance is a little bit that way and a little bit that way. So the variance is going to be, let's call it 3. I don't know because I haven't labeled my axes. But there's like a few points here, a few points here. They're all kind of clustered around this central point along the x1 axis. So the mean's going to be somewhere between this overlapping points A and D. Now, once we rotate the axes along this z1 axis, we actually now have a much larger variance. So again, our sort of average point is approximately going to be along the z2 axis. That will not necessarily be true in general, just happens to work here in this example. But we will have a mean sort of here, and clearly we've got quite a big jump that way and quite a big jump this way. So what we've done there is actually rotate the axes. We've picked a principal component that will actually maximize the variance, because generally larger variance means your data is being separated into these distinct clusters, and that is going to be our way in to explore the data, to understand the data, and to try and find groupings within our data. So to summarize what we've worked out before I go through the general method is 1. We want our principal components to be a linear combination of the variables. And 2, we want to pick our coefficients alphas, this vector alpha, we want that to be chosen such that the variance in our data along that axis is maximized. So 1, linear combination of the variables, and 2, we want that choice of linear combination to maximize the variance. Next up will be the full derivation and explanation of the method of principal component analysis, but first let's talk a little bit more about that data analyst master's course from Simplilearn. Simplilearn is the world's #1 online digital skills training platform for technology, business and programming. The Data Analyst Master's course, in collaboration with IBM, has over 38,000 learners to date and a 4.6 rating, making it the #1 ranked data analyst course by Career Karma. The program lasts for 11 months, covering topics in Excel, Python, SQL certification, and the statistical language R. During step 5 of your journey, you will be introduced to some of the most important tools for any data analyst, including the topic of today's video, principal component analysis, as well as clustering. You will work through examples in the live classes covering real datasets on college applications and breast cancer. After class, there are further practice exercises for you to have a go at, including a dataset which documents unemployment across the US. And if you want to practice even more, the unassisted practice exercises provide further problems for you to solve around the distribution of funds from a fictional NGO and investing in the stocks of pharmaceutical companies. The next cohort starts on Saturday, so be sure to sign up quickly before places run out. All of the links you need are in the video description, along with the discount code TRM20, which will give you 20% off the course fee when you talk with a learning advisor. You can also scan the QR code on screen. Happy learning. Suppose we have a dataset with, let's say, p variables, so x1, x2 through to xp. Then, according to step 1, which we've derived, we are going to want a linear combination of those variables. So we can start by saying let z1, which is going to be our first principal component, which of course we need to work out, and it's going to be equal to alpha 1, 1 times x1 plus alpha 1, 2 times x2 plus dot 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 plus alpha 1p times xp. So the 1 here in our coefficients alpha, this first one for all of them represents the fact that we're looking for our first principal component. And then the second label here, 1, 2, and p, tells us which variable, which x we are referencing. So this is now a linear combination of our variables. So we can tick that one off straight away. This is the general form. But because we have so many dimensions, so many variables, it's actually going to be easier to work with vectors. So we can rewrite this now and say, well, z1 is actually equal to alpha 1 transpose times x. And this is where we define alpha 1 as a vector is just alpha 1, 1, dot, 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 up to alpha 1p. Just contains p values, p-dimensional vector, and x is exactly as we would expect, x1, x2, dot, 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 up to xp. So that's the value of each of those variables. In fact, with the way I have written the vectors on the board, these would both be the transpose of our vector. So our vector is going to be vertical, because then if we have this one multiplied by the vertical x, we're going to get exactly z1. The line written above, and z1 of course here is a scalar. So the product of these two vectors in this form will give us our first principal component, z1. Now step 2 tells us we want to maximize the variance. So this is what we're going to use to determine our coefficients alpha. So the x's here are fixed, they are the variables, that's the data, but the alphas we are free to pick at this point. So we want to pick them to maximize the variance. So we want to know, well, what is the variance of Z1? What is var of Z1? And for this, we're going to have to do some statistics. Now, if our variables x1 through to xp are independent, they do not depend on one another, is the classic statistics or probability approach from a theoretical perspective, which means it's probably not true in real life and we're dealing with real data. But if they are independent, then we can say if independent, it's nice and easy. Simply can say that the variance of Z1 is just, it's almost linear, which means you just do alpha 1, 1 squared, you square your coefficient, and then it's times the variance of x1 plus dot, 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 all the way up to alpha 1 p squared times the variance of xp. So as long as we know the variance of the individual variables, then we can do this, again provided they are independent, which of course isn't going to be true in general, or hardly ever true, particularly as we are trying to actually explore the data here, so we can't assume that. That would be a very big assumption if we don't know much about the data. So we want to think more generally, what is the variance here? And when I say more generally, what that's going to mean for non-independent variables is there will also be some covariance terms. So we actually need to think about what happens when you have two variables, which I'll call x and y. So this is a measure of the relationship and the interdependence between those two variables. And this is actually defined in a very similar way to the variance. So the covariance of x and y is the expected value of x minus e of x, so that's x minus its mean, multiplied by y, also minus its mean. Now, for those of you that are familiar with statistics or probability, you may recognize that if I were to replace y with x, so the covariance of x with itself, then you would get the expected value of x minus e of x squared. And that is exactly how we define the variance. So the covariance is just a more general version of the variance where we are allowed these two variables to differ. If we now expand this expectation, we are going to get the following. So it's the expected value of xy there minus x times e of y minus e of x times y, and then plus e of x times e of y. Using the properties of expectation and taking this through, we're actually going to get e of xy minus e of x times e of y. So the expected value of e of y is actually just the same thing. It's just e of y again. Minus another lot of it, and then plus one more lot. So that's just minus one lot of it, in fact, when we simplify everything. And now this, again, if you're familiar with the definition of independence of two variables, so if x and y are independent, that actually means that e of xy is exactly equal to e of x times e of y. We can split up those two terms in that product. So that is going to be true when independent, and that's why the covariance is 0, and that's why this one does not have any covariance terms. So generally they would be there, but because of the independence, all of the covariance terms disappear. However, in our situation, we are not assuming independence. And so we're going to actually have to calculate these covariances and think about how they make their way into this formula for non-independent variables. So when our variables are now dependent, and we want to include these covariance terms, what we're going to find is the following. So we still get all of these initial terms being added together. So I'm just going to use a little shorthand here and call this from I equals 1 to p, what we've got is alpha 1I squared times the variance of xi. So again, that's all you get when they're independent, but we also now get these covariance terms. So when we bring in the covariance, we're actually now going to get the sum from I equals 1 to p, and the sum from j equals 1 to p of alpha 1i times alpha 1j times the covariance cov of xi comma xj. So you can clearly see that in the case of independent variables, when the covariance is 0, this term vanishes, and then we just have the sum of the coefficients squared times the variance, which is exactly what I wrote here in that simplified case. But now we're going to include this general term because we are not going to assume independence, so the covariance could be non-zero. So you'll see we've got the same structure here. The covariance of xi and xj could be written as cov of x1 and x1 would actually just be the variance of x1. So really we're just looking at all pairs of terms being compared here, and we sum over the two of them because here we had a squared term, so this is alpha 1i times alpha 1i. So here, because we have xi and xj where they differ, I should also add I is not equal to j, because we've already, that case for I and j being the same is actually the variance. So here we actually have the covariance, and we have these two coefficients, which is coming out here as the squared when I and j are the same. So this is the general form of the variance of a linear combination of our variables where they are not necessarily independent. And now we want to use this, or we want to take our vector form over here, I should say, and think about what does this look like using this definition, this full definition of the variance of a linear combination of variables. So looking at the formula we have over here, the fact that we are summing over both I and j, and we're taking a covariance of xi and xj, it's kind of hinting at a matrix. And again, if any of you watching are familiar with linear algebra or matrices, you may have thought that this was going to come into our formula that we're going to get now. And that's exactly the case. So what we've really got here is the variance of Z1 is equal to, we've got an alpha transposed, and then we've also got an alpha 1 at the end. So that's going to ensure that we get the alpha squareds in the relevant places. But in the middle, we have something called the covariance matrix, which I'm going to label S. So S is equal to the covariance matrix. The ijth entry of our matrix is actually just the covariance of xi with xj. Exactly what we're seeing here. And on the diagonal, this will be the covariance of xi with xi. And because it's the diagonal part of the matrix, we're going to get the same alpha term from those two vectors. So that's why we get the squared. But for the off-diagonal terms in S, we're going to pick up the alpha 1i from the first one and the alpha 1j from the second one. And so we are going to get this exact term. Now at this point, I would recommend, if you're not familiar with matrix notation, or you've got a bit lost as to how I've ended up with this formula for the variance, I would recommend maybe trying a simple two-dimensional case. So take two variables, x1 and x2. Convince yourself that the variance of alpha 1 x1 plus alpha 2 x2 would look like this. Obviously in a simpler form, you're only going to have two terms in here and a couple of other terms in there, two terms in there, and then write out your 2x2 matrix S. Just convince yourself that these two are the same. If you're familiar with matrices and vectors and linear algebra, hopefully this makes sense. But if not, don't worry. We're just going to use this formula now to actually derive our principal component analysis method. So we have our general linear combination of the variables given by Z1 is alpha transpose times X, where alpha is to be determined. And then we have that the variance of this linear combination, which we just worked out, is alpha transpose times S times alpha. Now, we want to maximize the variance. We want to make this as big as possible, and that's going to determine what our coefficients alpha need to be, what that rotation is, if you will. However, looking at this formula, this vector form, or even going back to the sum that I had on the board earlier, all of the terms just had alphas in front of them. So in a way, this is maximized by just making alpha as big as possible. It's actually unconstrained in a way, because as alpha increases, this just goes up, which doesn't really help us. But this is where that earlier condition, which I said was just a convention, or one way to think of it as a convention, that we want alpha to be a unit vector, that's actually what we're going to use to constrain the problem and to help us then maximize the variance subject to that particular constraint. So what we want to say is that we want to constrain the problem by specifying that alpha is a unit vector, so that means alpha 1 transpose times alpha 1 has to give us 1. So the vector has length 1. Now again, if we think about the fact that alpha is really just a rotation of our axes in whatever dimension we may be working in, p dimensions here, but really it's just a rotation of those axes, then the size of alpha is actually irrelevant. It's the ratio of those coefficients that tells us how much of each variable to take. So applying this constraint will not fundamentally change the procedure that we are trying to go through here. So by specifying that alpha just has any arbitrary finite length, why not pick 1, make it a unit vector? By specifying that, it will actually not change the outcome, but it will now allow us to have a constrained problem which we can now apply a maximization procedure to. And so we can actually solve this using the method of Lagrange multipliers. Now, this is a method from calculus, and because this is a statistics or a machine learning data analysis video, I'm not going to go through the details of where it comes from, why it works. That's a whole other video. Probably should add that to the Oxford Calculus series, note to self. So I will just spell out the key concepts and how it works, and then we will apply it. But fundamentally, the method of Lagrange multipliers allows you to find a maximum or a minimum of a particular function. So this is going to be our function when you have a constraint. So here's how it works. We want the method of Lagrange multipliers. So generally, what we want to do here is maximize, and again, this would work for minimizations as well, but we want to maximize some function f subject to a constraint, and we'll call this constraint g, and let's suppose that g is equal to some constant c. Now, the method of Lagrange multipliers says the way we do this is you form a function which is usually labeled capital F, or at least that's how I teach it in my undergrad calculus class. You define f to be the function we want to maximize, lowercase f, minus lambda, and then we put g minus its constant in there like that. So in some sense, you just rearrange your constraint to be g minus the constant equals 0, and then just throw that one in your function. And then what you want to do is actually calculate the partial derivatives of f. So you want to solve all partial derivatives of f equal to 0. Of capital F equal to 0. So there you're going to be differentiating with respect to your variables. So, you know, it might be x, y, and z if you're working in 3D, for example, like a geometry problem. So you would differentiate f with respect to x, y, and z, set those to 0. But you also set df by d lambda equal to 0. So that will actually just give you back your constraint. So that's actually just equivalent to saying that g must be equal to c, but it's just handy to kind of think of it in this partial derivative context. So lambda here is your Lagrange multiplier, That's just some variable we introduced to help us solve this problem. So again, I'm not going to go through the details of why this works. That would be a calculus video. But you form this intermediate function, which we'll do in a moment. We then calculate all of the partial derivatives equal to 0, and then we solve that remaining system. So we then solve the system of equations. And that will give us the answer. So this might make more sense when we see it in practice, so don't worry if you've never seen it before. If you have seen it before, probably a good time to refresh your knowledge of Lagrange multipliers, because what we're going to have to do now is think about what this process or procedure looks like when applied to these vector forms. Applying the Lagrange multiplier method to our constrained problem, we will have the following. So our capital F, as I have called it over there, is going to be equal to the function that we are trying to maximize, which is the variance. We want to maximize the variance. You can give that one a tick now, because that's what we're doing with Lagrange multipliers. And to maximize the variance, so F is equal to alpha 1 transpose times the covariance matrix times alpha 1. And then the constraint is G is this, is equal to 1. 1's our constant. So minus lambda times alpha 1 transpose alpha 1 is equal, not equal to, minus 1. So again, G minus the constant. This is G minus 1 goes in here, and then we form this function F. So now the method, having done this, says solve all the partial derivatives equal to 0. Now when I was discussing this, I mentioned they might be like x, y, z partials, but here we're trying to actually solve for alpha. So our variables, just to kind of stress that, the variables here are those alpha values. So they are alpha 1, 1, alpha 1, 2, all the way up to alpha 1p. So we want to take the partial derivative of this function, capital F, with respect to each of these variables and set it to 0. However, given that this is written in vector form, we can actually also write the partial derivatives in vector form. So what I mean by this is we want to take the gradient vector. So again, don't worry if you don't have that much calculus knowledge and you're unsure what the gradient vector is. It's just a vector where each component is a partial derivative. In short, you should also check out my video I made on the gradient vector in the Oxford Calculus series. I will pop that up in the cards and also link it in the video description box. But don't worry, you don't need to know too much about it, though that might be helpful if you're trying to really understand what's happening. We're just going to use it. So we'll work out what this looks like in a moment, but that needs to be true for this. We also want df by d lambda to be 0, but as I said here, that's just the same as our constraint. So that must be true. We also want alpha 1 transpose alpha to be equal to 1. And then we want to solve that system of equations. So what is the gradient of this function f? Rather than just telling you what we get when we take the gradient of this function f, I think instead I will actually do an explicit example with, let's say, a 2 by 2 matrix. So let's suppose that f in the 2D example case is going to then be given by alpha 1 transpose, so let's just write that as alpha 1, alpha 2, our two variables, times our matrix S, so that's going to be S11, S first row, second column, S second row, first column, S22. And then we've got minus, then multiply by alpha 1, so it's alpha 1, alpha 2 there. Then we minus lambda times alpha 1 transpose times alpha gives me alpha 1 squared plus alpha 2 squared minus 1. Okay, so this is an explicit f in the case of two variables, and therefore we only need to work out two coefficients, which I've labeled alpha 1 and alpha 2. So expanding that out, first row, first column is going to give me alpha 1 S11 plus alpha 2 S21. First row, first column, and then first row, second column, comma, alpha 1 S1 2 plus alpha 2 S2 2, and that's then multiplied by alpha 1 alpha 2, and then still minus this whole thing on the end, 2 squared minus 1, and then finally expanding that out. So this is our explicit f in the case of two variables where we're just trying to find one principal component. So if we want to work out the gradient of f, then what that's actually going to be is just df by d alpha 1. Derivative with respect to the first variable is in the first position of our gradient vector. And then df by d alpha 2, that second component, and we want this to be equal to 0, 0. We're going to get 2 alpha 1 S11 plus an alpha 2 of S21 plus another alpha 2 of S, that should be 1, 2, shouldn't it? So I think the reason I've written that as 2, 1 is it turns out that this matrix S will actually always be symmetric. So the covariance of x1 and x2 is always equal to the covariance of x2 and x1. So these two are actually, they're always equal. So clearly my subconscious has already written them as being equal, but I'll keep it general. Alpha 2 S21 plus alpha 2 S12 from that, and then the last term doesn't do anything. And then by alpha, oh, and then we have the last term, don't we? Don't forget that, minus 2 lambda alpha 1, and then we're good. Comma, it's going to be very similar now. It's going to be, start on that one, we get 2 alpha 2 S22 plus alpha 1 S21 plus alpha 1 S12, and then minus 2 lambda alpha 2. So if we look carefully at the gradient vector we have here, compared to what we have at the top of the board, where we're using the matrix and vector notation. That's what we want to try and get here for the gradient. That would be S11 times alpha 1 plus S12 times alpha 2. S11 times alpha 1 plus S12 times alpha 2. And again, because it's symmetric, these two here are actually going to be the same thing. So that's why we can just group that as two of the same thing. So I should also add that since S symmetric. Now the second term in both of these is then actually just a minus 2 lambda times the vector. So what we've ended up with is that the grad of f, and we've done this explicitly for a two variable example, grad of f is actually looking like this. And this will be true in general. Okay, I haven't proven it, but if you were to take this and generalize to a p by p matrix and a p vector, you're going to get the same result here. So now we're going to use this and solve this equal to 0 to try and work out what does alpha have to be. So our Lagrange multiplier problem has reduced to these two equations. The gradient of f, those partial derivatives with respect to alpha being 0, means that this must be true. And we have the constraint that we want this to be a unit vector. Now, some of you watching may recognize, or may have spotted what is happening with this equation. So if I cancel the 2 and then rearrange that equation, what we've actually got is s times alpha 1 is equal to lambda, and I'll put a 1 on that, times alpha 1. This is the eigenvalue equation. So this is the eigenvalue equation for the matrix S. But what was S? Well, S was the covariance matrix. So for S, which is the covariance matrix. So what this means is that in order to find alpha, which remember is the linear combination, the amount of each variable that we want in our rotation, to find alpha, we actually just have to find the eigenvalues of S, that will be lambda 1, so lambda 1 equals an eigenvalue of S, and alpha 1 is actually the corresponding eigenvector. And we've also normalized that, so where it has length equal to 1. So all of a sudden, from talking about a problem in statistics and data analysis and machine learning, we've actually reduced this now to a problem in linear algebra. So this is why throughout I was very keen to talk about things using matrices and vectors, because you get this really, really nice result that comes out at the end. So in order to find our principal components, what we need to do is solve this eigenvalue problem. So you proceed in the usual way. So to find the eigenvalues, what we do is we solve the characteristic polynomial, which is that the determinant of s minus lambda times the identity, we want that equal to 0. That then gives us a polynomial in lambda, and then we solve the roots of that polynomial, give us the eigenvalues. So this will be a pth degree polynomial, and therefore we'll have p roots. So we will get there those p different eigenvalues from solving this equation. And then you substitute back into here, and we solve for alpha to get the corresponding eigenvector, and that is going to be the principal component. That's going to be the rotation that we want. Now, if you are unfamiliar with linear algebra and eigenvalues, eigenvectors, and you look at this equation and don't really know what's happening, again, don't worry. I have a whole series of videos in the Oxford Linear Algebra series which will tell you all about this, including a specific video just looking at how do we find eigenvalues and eigenvectors of a matrix. But for here, we can just say, I will just state that we can solve this and get our eigenvalues. So we then solve to get the eigenvalues, lambda 1, lambda 2, through to lambda p, and their corresponding eigenvectors. So each one will have a different eigenvector. So this will be alpha 1, alpha 2, up to alpha p. So now the question is, well, which one of these eigenvectors is actually the one we want? Because each of these, it turns out, will be one of the principal components, but remember, we want the particular one over here that's going to maximize the variance. So in order to see that, we do a final manipulation of our equation at the top of the board. So if I take this equation, the eigenvalue equation here, and I pre-multiply, which means on the left-hand side, by alpha 1 transpose, then what we have is alpha 1 transpose s alpha 1 equals alpha 1 transpose lambda alpha 1, lambda 1. Lambda 1 is just a scalar, so we can pull that out. So then that's lambda 1 times alpha 1 transpose alpha 1, but we said that that was 1, right? That was our constraint over here. So this is actually just equal to lambda 1. Alpha 1 transpose s alpha 1, as if by magic, that's our variance. So the variance of the principal component z1 is actually just given by lambda 1. So if we want to maximize the variance, what we want to do is pick the largest possible eigenvalue. So therefore, lambda 1 is the largest eigenvalue of S, the covariance matrix, and alpha 1, which remember is the vector of coefficients that's going to give us the answer, give us that principal component, that first one. Alpha 1 is the corresponding eigenvector. So to summarize, the principal components are actually just given by the eigenvectors of the covariance matrix S. So, summary. The principal components, the PCs, are the eigenvectors of S, and we take the first principal component is the eigenvector corresponding to the largest eigenvalue. So in other words, the principal component analysis just relies on first calculating our covariance matrix S for all our different variables, work that out, which can be done using the data. Then we solve the characteristic polynomial to get the eigenvalues of S and their corresponding eigenvectors. And we order the eigenvalues by size, and the largest eigenvalue, the eigenvector that corresponds to that, mentioned over here, is going to give us that first principal component, which is going to be the rotation we make up here to give us Z1. And all of the others will actually follow in the same way. So the second principal component is going to be the eigenvector corresponding to the second largest eigenvalue of S, and so on and so forth. As a final little nugget, taking some of my favorite theory from linear algebra, because the covariance matrix S is symmetric, which just follows from its definition, then we actually know that there will exist a basis of eigenvectors, and we can in fact diagonalize S. So what this all means is that we can actually write S is equal to V times D times V transpose, where D is a diagonal matrix, and along that diagonal it just has the eigenvalues, like so. And this is where we have ordered them. So lambda 1 is greater than lambda 2 is greater than ... is greater than lambda p. So putting them in order to make sure we have the correct eigenvector, the correct principal component. And V is actually just made up now of alpha 1 in this first column, alpha 2 in this second one, all the way through to alpha p. So the columns of our matrix V are actually the eigenvectors. So i.e. the columns are the eigenvectors. And so practically, what this actually all means for our data, for our analysis, our data exploration, is the following. If we have data Y, and so Y here will be an n by p matrix, which means we are taking n observations of our p variables, n observations of p variables. Then the transformation that we want to make is simply Z is equal to Y multiplied by V, where V is this matrix. V is the matrix constructed by our principal components, where those columns are the ordered eigenvectors of the covariance matrix S. And this matrix Z, which is just Y times V, is called the scores matrix. So in practice, you will have your data Y that you want to analyze, you want to explore. You will compute the matrix V through all of the methodology I've just discussed, which ultimately means finding the eigenvectors of our covariance matrix S, ordering them correctly, of course. Once you've found V, you multiply your data Y by the matrix V to get the scores matrix, and this will contain your principal components. This is what you're going to plot, and this is going to identify any of those patterns or clusters in your data. And that's it. A full explanation and derivation of principal component analysis with some assistance from the Simply Learn Data Analyst Masters course. Don't forget to check out all of the courses available from Simply Learn using the links in the video description. And if you use the code TRM20, that's TRM20, then you will get 20% off for any of those courses that you sign up for. Thank you everyone for watching. Please do subscribe for more maths fun, and I'll see you all very soon. Take care.